To enhance the grounding of a three-phase, three-wire, 240-volt, 600-amp service, several key steps can be taken. Firstly, install a grounding electrode system. Drive two ground rods at least 8 feet apart. These rods should be connected together using a 6 American wire gauge copper conductor. Secondly, bond these grounding electrodes to the current transformer, or CT, enclosure. Use a 6 American wire gauge copper conductor to make this connection. Next, consider installing a ground loop conductor. Run a 6 American wire gauge copper conductor from the CT enclosure around the perimeter of the building. Connect this conductor to the ground rod at one end and the electrical service entrance at the other end. Then ensure that all metallic piping systems entering the building, such as water, gas, and electrical conduit, are bonded to the grounding electrode system at the point of entry. For non-metallic piping systems, like polyvinyl chloride or PVC, and cross-linked polyethylene or PX, use grounding clamps to bond them to the closest metallic piping system. After completing these grounding improvements, it's crucial to test the grounding system. Perform a ground resistance test to verify that the system meets the required grounding resistance value, which is typically less than 25 ohms. In addition to these grounding measures, there are other considerations to keep in mind. Verify the current ratings of the circuit breakers and fuse disconnects. Ensure they are appropriate for the load being served. If the 4/0 conductor feeding the water line is insufficient for the current load, consider upgrading the wiring to meet the required ampacity. Installing surge protective devices is also recommended to protect the electrical system from voltage spikes. Finally, consult with local building authorities and electrical inspectors. This ensures compliance with all applicable codes and regulations. A comprehensive grounding system is vital for electrical safety and proper equipment operation. The grounding electrode system is the foundation of electrical safety. It provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly clear the fault. Ground rods, typically made of copper or copper-clad steel, are driven into the earth to establish a connection to ground. The National Electrical Code or NEC specifies the requirements for ground rod size, material, and installation depth. The 8-foot spacing requirement between ground rods is important to minimize the overlapping of their effective grounding zones. The 6 American wire gauge copper conductor connecting the ground rods ensures a reliable path for fault current. Bonding the grounding electrodes to the CT enclosure is essential. This connection ensures that the metal enclosure is at the same electrical potential as the ground, reducing the risk of electric shock. The 6 American wire gauge copper conductor used for bonding must be properly sized according to the NEC, based on the size of the service entrance conductors. The ground loop conductor, also known as a grounding ring, provides an additional path for fault current to return to the source. By encircling the building, it helps to equalize the ground potential throughout the structure, further reducing the risk of electrical shock. Metallic piping systems can become energized due to faults in electrical equipment. Bonding these systems to the grounding electrode system provides a safe path for fault current to ground, preventing them from becoming a shock hazard. Grounding clamps are used to make a reliable connection between the metallic piping and the grounding conductor. Non-metallic piping systems do not inherently conduct electricity. However, they can still pose a shock hazard if they come into contact with energized components. Bonding them to the closest metallic piping system provides a path for fault current to ground, minimizing this risk. The ground resistance test measures the resistance of the grounding electrode system to earth. A low resistance value indicates a good connection to ground, ensuring that fault current can quickly and safely return to the source. The typical requirement of less than 25 ohms is specified by the NEC and other electrical codes. It's crucial to use a properly calibrated ground resistance tester and follow the manufacturer's instructions for accurate measurements. Verifying the current ratings of circuit breakers and fuse disconnects is essential for overcurrent protection. These devices are designed to interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. The current rating of the circuit breakers and fuses must be appropriate for the load being served, as determined by the NEC. If the 4/0 conductor feeding the water line is insufficient for the current load, it can overheat and potentially cause a fire. The ampacity of the conductor, which is the maximum current it can safely carry, must be determined according to the NEC. If the conductor is undersized, it should be upgraded to a larger size to meet the required ampacity. Surge protective devices, or SPD, protect electrical equipment from voltage spikes caused by lightning strikes, utility switching, and other transient events. These devices divert the excess voltage to ground, preventing it from damaging sensitive electronic components. SPD should be installed at the service entrance and at downstream locations to provide comprehensive surge protection. Consulting with local building authorities and electrical inspectors is essential to ensure compliance with all applicable codes and regulations. Electrical codes can vary depending on the jurisdiction, and it's important to follow the specific requirements in your area. Electrical inspectors can provide guidance on grounding and bonding requirements, as well as inspect the completed installation to ensure it meets code. Implementing these measures will significantly improve the grounding of the electrical system, bringing it up to current code requirements and ensuring a safer electrical environment. Proper grounding is not a one-time task, it requires regular inspection and maintenance. Regularly inspect the grounding system for any signs of damage or corrosion. Tighten any loose connections and replace any damaged components. Retest the ground resistance periodically to ensure it remains within acceptable limits. Keep records of all grounding system inspections, tests, and maintenance activities. This documentation can be helpful for troubleshooting problems and demonstrating compliance with code requirements. By following these guidelines, the electrical system can be maintained safe and reliable for years to come.